Hello guys and welcome to another past paper video. So today we are looking at another March 2024 paper because previously we've done the March 24 IGCSE paper 42. Now we are looking at another one and this one is IGCSE paper 62. So that's what we are looking at today. Now if you guys remember, then with the paper, what do you call it? With the paper 42, my advice is that even O-level students should try it out because there are some minor differences. But with the ATP paper, which is paper 62 for IGCSE, what is called paper 4s for your O-levels, there are literally no differences. So for the O-level students, this is great practice material. It's also going to give you an idea on how well you're doing with respect to time and all of that stuff. So let's get right into it. So the first question, all right, so yeah, this paper is also not going to be a solution. This is a walkthrough because I've solved all of the paper beforehand. I'll just be going over my solution and talking about some common mistakes that people make. So a student determines the mass of a meter ruler by a balancing method. He is using the apparatus shown in 1.1. So there's the meter rule, there's a load which is placed. This is the 0 cm mark. This is the pivot, right? So we try to balance this meter rule. Part A, the student places a circular load on the meter ruler as shown in 1.2. Determine the distance d of the center of the load from the zero end of the ruler. So this is how the scale goes. So we need its distance till this midpoint. So given the diagram, I could read off the left end, which was at 26.5. The right end was at 29.5. So just taking the average of the two gives us the midpoint, which is the center, which turns out to be 28. But because we are using a meter ruler, which can read to one decimal place, I would write this as 28.0 centimeters. The student adjusts the position of the meter ruler on the pivot until the meter rule is near as possible to being balanced. Describe a technique for ensuring that the ruler is as near as possible to being balanced. So the idea is that you just either move the pivot or the rule along this point to which the ruler just tips maybe in a certain direction. Then you can see when it tips in the opposite direction, and you can basically look at the positions of the pivot at those points, at what length, basically at what position the pivot is placed, and you can average out those positions to get the midpoint, which is where it should ideally be balanced, right? So this is how you find, uh, this is how you ensure that the ruler is as near as possible to being balanced. Part two, student finds the ruler is as near as possible to being balanced when the pivot is at this 47.6 centimeters mark. Calculate the distance A of the center of the load from the 50 cm mark. So you have to use this equation. B is what you calculated from the previous part. So 50 minus 28, again, I'm going to write this as 22.0. Calculate the distance B of the center of the load from the pivot as shown. Use your value of D from A again and this equation. So position of pivot was given as 47.6. I subtract 28 from this and I get this answer. So this is my B. The student moves the load so that its center is above the 5 cm mark and balances the meter ruler. He repeats the procedure for the load at the 10, 15, 20, and 25 cm marks. And the position of the load, the A values and the B values are shown in this table. Plot a graph of A on the y-axis versus B on the x-axis. You do not need to start your axis from the origin 0, 0. So basically you can use a false origin here. So if you look at the A values, these are pretty nicely spaced, starting from 25 and then with equal gaps of 5. So this is exactly what I can select as my scale values as well. So 25, 30, 35, 40, 45. The B values, these go from 22.5 to 40.5. So these are not as nicely spaced. So I should take the starting point of the scale as a value slightly lower than this, and the ending point as a value slightly higher than this. So I'm thinking from 20 to 45. Just like how this is from 25 to 45, this one would be 20 to 45. So first off, I select my axis. Now, when I was doing this paper on my own, first I did this, that I kept this as 30, this is 35, this is 40, and this is 45. So I was seeing that only half of my y-axis is being used up by the scale. So I just double all of this. So instead of one box away being 30, I take two boxes away being 30, and that's how I make my y-axis scale. And for the x-axis scale, the labeling was just discussed. Also, there are also marks for this, that whenever you are supposed to use a graph grid, do not have your values further than two boxes away marked. So what I mean by this is, if you mark 20 here, don't mark 30 here. This will cause you to lose marks. So the max further away reading should be like two boxes away, 2 centimeters away. So after 20 comes 25, then two boxes away 30, then two boxes away 35, then 40, right? So my 40.5 value would be plotted really nicely. Then I just plot these values according to the scale I've chosen. I can see what each small box equals. So at random, if I talk about the plotting of any point, let's take something which is sort of difficult to look at. Let's take this one. So A is on the y-axis, B is on the x-axis, so 35.2 on x, 40.0 here. So 35.2 means, if I look at the scale, so right in the middle would be 37.5. And this one would be 35.5. So 35.2 would be approximately in the middle, and this is 40. So this is how I plot all my points. Then to make the best fit straight line, so the idea of the line of best fit is that this line is as close to as many points as possible. It doesn't necessarily even have to go through a point. Just the idea is this, that it must be as close as possible to all the points. Another sort of criteria you can use to see whether you've gotten a good line of best fit is to ensure that there is an even distribution of points above and below the line of best fit. So approximately the number of points you have above should be equal to the number of points below. Obviously, these are 5 points, so I can't ensure a exact fit, right? Because 5 is not an even number. But you can see that this line, this point is really close. This one is slightly further away from the line. This one is closer still. So both of these kind of like balance each other out, these 3 points. And then this one is slightly above, this one is slightly below. So this is how I get the line of best fit. Always draw the line of best fit from covering all of the grid, right? So it should be going all the way from the start to the end. Even if you don't have values beyond 40.5, the graph should cover all of the grid. Determine the gradient of the graph. Show clearly on the graph how you obtained the necessary information. So gradient is change in y over change in x. I just need 2 points. Again, when you do have the line of best fit, those do look at those points which very clearly lie on the line. So for example, this point was right on the edge of a box, so I took this. So if I read this off, this would be 40.5, 41, 41.5, 42. So this is 42. And because each of these 5 small boxes on the y-axis are 2.5, this is 47.5. Similarly, on the x-axis, I take another really clean point here, which is 22.5, 23, 23.5, 24, 24.5, and right in the middle of 25 and 30, this is 27.5. Another thing to take care of while selecting points for the gradient is that these points must be greater than half the length of the line away. So you should preferably take one near to the top and one really near to the bottom of the line. Then I just use change in y over change in x. So 47.5 minus 27.5 over 42 minus 24.5. So my answer turns out to be this. If you think about the units here, so because gradient is y over x, so centimeters over centimeters. So by the way, this has no units. All right. It has no units, and this is what will be sort of used in this next part. Calculate the mass m of the meter ruler using this equation. M equals k over g minus 1. K is given as 25 grams, so we have the unit here, but the gradient has no units, so it's just the value. So whatever is the unit of the numerator would also be the unit of this entire fraction. So since this was in grams, this is also going to be in grams, and then I just plug this into the formula. The accuracy of the result obtained by this procedure depends on the meter ruler without a load balancing with the pivot at the 50 cm mark. A student finds that this does not happen, as it almost never will in a proper experiment. She adds a small piece of modeling clay to one end of the meter ruler to correct it. Suggest if this is a suitable change and explain your answer. Now in this one, let's say that how my ruler was placed, maybe it's falling like this, right? So to create this clockwise movement, I place some modeling clay here. This is wrong because this load that I placed, this was basically opposing the moment which would be produced by the weight of the meter rule, right? And this load we did take into account into our calculations. But if now again I place another mass, which I'm not really accounting for in my calculations, this is not going to give me a correct answer, right? So this is wrong. So let's look at the reasoning written for this, right? Because it will cause the ruler to tip another way. It's going to create some moment of its own. So this is not correct. So I will say that the modeling clay creates a moment of its own. So it's basically just a load as well, which we are not accounting for in our calculations. Question 2, a student investigates a circuit containing different combinations of 3 resistors. She first uses circuit A as shown in 2.1. On 2.1, draw a voltmeter connected to measure the potential difference between P and Q. So voltmeters are connected in parallel. That's what I've done. The student measures the potential difference for terminals P and Q and measures the current I in the circuit. Meters are shown in 2.2 and 2.3. Again, if you've been doing some of the recent papers, you know that the next question is going to be for you to read off these values. So this would be right in the middle, 3.5. So it's 3.1, 3.2, 3.3, 3.4, 3.5. So this is 3.1 volts. Between 0 and 0.2, this is 0.1. So this one would be 0.12 amperes. So those are the values that we get. So in the first line of the table, we have to record the values shown. Part C, circuit B, the student connects the resistors between terminals P and Q, and now it's in a different way. If you guys know your theory, this is 2 in parallel, which is going to be in series with the other resistor. And circuit C, where you have all of these 3 in parallel. Part 1 says calculate and record in table 2.1 a resistance R for each circuit. Use the values of V and I from 2.1 and the equation R equals V over I. So since I have all of these V over I can just use R equals V over I and calculate all of these resistance values. So these are what they turn out to be. You also have to add units to the column heading. So voltage would be in volts, current in amperes, resistance in ohms. Again, this is also just really easy maths right now. Calculate a resistance RA, use the value of R from circuit A and this equation. So R from circuit A is 25.8. I just have to divide this by 3 and write down the answer. It turns out to be 8.6 ohms. Similarly, RB, for this you use the value of R from circuit B, which is 13.2. You divide this by 1.5. And similarly, the last one, you have to use the value of R from circuit C. So RC is 3R. So 3 times this value. 3 times 3.02 must be 9.06, which it is. And now we have all of these values for the resistances RA, RB, and RC. A student suggests that RA, RB, and RC are equal. State whether your results support the suggestion. Justify your statement with reference to values from your results. You know that how we justify whether values are equal or not is by saying whether these values fall within 10% of each other or not. So what I've done is I take the smallest value, 8.6, and I take 10% of this, which is 0.86. So the maximum deviation which could be there is that if it's 8.6 plus 10% of it, which is 0.86, which turns out to be 9.46. But these values are less than 9.46. So for the experimental purposes, these values are equal, right? So I'll say that these values are equal because all of these values are within 10% of each other, right? This is the math behind my reasoning. Part E, a student investigates the circuits in the resistors in circuit A using a variable resistor to change the current in the circuit. Part 1 in the space below, draw the symbol for a variable resistor. Very straightforward. Suggest one advantage of using a variable resistor to change the current in the circuit. The first thing that comes to mind, if you have done some electricity experiments, is that with these resistors, you have these combinations which you need to take apart and plug it in into the circuit to change those resistor values. And obviously, those values can only be just some values. So for example, with 3 resistors, you can mentally think that you can only form 4 different combinations. 2 of these are all 3 in parallel. Another one is all 3 in series. Then you can have 2 in parallel in series with another one, and you can have 2 in series in parallel with another one, right? But with a variable resistor, you can select many values and you can basically have many different resistance values and you can get a lot of current values as well. So these are the advantages of using a variable resistor. You can write any one. Question number 3 is on lenses. Student determines the focal length of a converging lens by 2 methods. So you have the illuminated object, you have some lamp which is casting light onto it. This light goes through a lens, and then this is incident on a plain white screen. The student sets up the apparatus as shown in 3.1. Suggests one precaution that must be taken when setting up the apparatus to ensure accurate measurements. So one of these, which is always asked in lens questions, is to ensure that the lens and the screen are perpendicular to each other and that all of these three, what do you call it? All of these 3 things, the object, the lens, and the screen are on the same horizontal level, right? These two are what you always write. You can write any one of these. In my answer, I've written both of these. Part B, the student sets the distance u between the illuminated object and the lens to 20 centimeters. So this length u is 20 centimeters. He places the screen near the lens and moves the screen until a sharp image of the illuminated object is seen on the screen. Describe a technique for obtaining an image that is as sharp as possible. Again, questions like these have been asked word for word in a lot of the older lenses past papers. The idea is that because in this one, you have this distance u between the object and the lens. So just because of this, you should not really move the lens in this case. Rather, you should move the screen back and forth and see where you have a sharp focused image forming here. So in this one, let's get rid of the lens because of how this particular experiment works. Measure V1, the distance from the lens to the screen on 3.1. So if you print this out and measure this, I did this, this turns out to be exactly 8 centimeters. And because this is drawn to 1/10 of the scale, so all the lengths are 1/10 of what they actually are. So the actual distance would be 10 times that. So 8 times 10 gives us 80 centimeters. Next part, shapes of the illuminated object and the image seen on the screen are shown in 3.2 and 3.3, and these are full size. Measure h naught, the height of the illuminated object. So this turns out to be 1.2, and this height hi turned out to be exactly 4.8 centimeters, right? So you can print this out and you can measure this for yourself. This is what it turns out to be. Part 2, calculate a value m for the magnification, which you know is image height over object height. So 4.8 over 1.2 turns out to be 4. Calculate a value f1 for the focal length of the lens. Use values from B2 and C2 and this equation. So V1 capital V1 was this 80 centimeters over m plus 1. So that is 4 plus 1. So 80 over 4 plus 1 is 80 over 5, which is 16 centimeters. Describe one difficulty that is experienced when using a ruler to measure the height of the image in this experiment. As with a lot of the lenses experiments, when you are actually measuring this height, the problem that you will encounter is that your hand will start to block some of the image which is forming, and that's going to make it difficult for you to measure this length, right? So that is the problem. So your ruler and your hand will block the light arriving at the screen. There could be multiple solutions to this. One of these is that you can just mark these points and then you can measure the length between them. Or another one is this, that if you use a translucent paper as the screen, then you can draw on that behind the screen, right? And you can then measure the length, which is going to get rid of this problem of the light being blocked, because then you'll be taking the measurements from behind the screen. Part F, student adjusts the position of the lens so that U is 40 now and obtains a new value V2, which is given as 25.1. Calculate a second value F2 for the focal length of the lens using this equation. So 40, 25.1 over 40 plus 25.1, which gives us F2 as 15.4. The next one asks, suggest which value is more accurate. Explain your answer. Again, this is a suggest part. There could be like 4 or 5 possible answers given that you give a good reasoning. The first thing that should really come to mind is how you have calculated these focal lengths. So for the focal length F1, what you did is that you first measured the heights, which you use to calculate the linear magnification, and then you use this formula, right? So here V1, what was V1? This was the distance from the lens to the screen. So it's this distance, right? And the next one, what's that? In the next one, you have to measure the distance from the object to the, what do you call it? From the object to the lens, which is 40, right? And you get a new V2 as well. So V2, if you think about it, V2 you had to find in both cases, right? Here you found out V1, now you found out V2. But the difference is that here you are setting your U to be equal to a certain value, 40.0. And if you think about this practically, this is not very easy to measure. What is much easier to measure are the heights of the object in the image. Because of this reason, I'll say that what I calculated using this method, which was F1, this is more accurate because the heights are easier to measure than U, right? So the heights are easier to measure than U here. All right, last question. Again, this question, I'm pretty sure we have had a question very similar to this previously. A student investigates the effect of insulation on the cooling of a liquid. Plan an experiment which will enable her to investigate how changing the thickness of insulation surrounding a beaker affects the rate of cooling of hot water in the beaker. Apparatus includes glass beaker, supply of hot water, a lid on the beaker, and strips of insulation which you can cut according to your preference. In your plan, list any additional apparatus needed. Obviously, to see how much it cools, I need one crucial thing which is not listed here, which is obviously a thermometer, right? That's what I need. Otherwise, I can't calculate how much the temperature drops by. Explain briefly how to do the experiment, including the measurements to take so that the rate of cooling can be determined. State the key variables to keep constant. Draw a table or tables with column headings to show how to display the readings. You're not required to enter readings. Explain how you use the readings to reach a conclusion. First things first, let's identify what we are changing, what is going to change as a result, and what we should keep constant. So basically, are independent, dependent, and control variables. We are changing the thickness of insulation, so that's an independent variable. As a result, the rate of cooling of hot water will change. That's a dependent variable. And everything that should be kept constant is a control variable. Some of the things that come to mind are the volume of the hot water, the temperature of the hot water. But there could be many more as well, as you can see here. So you vary the thickness and measure the drop in temperature from the thermometer. So volume or starting temperature must be constant. Additionally, you can also say that the dimensions of the container, the texture, color, this must be constant. You can also say that the room, this environment that you are conducting your experiment in, the temperature of that room, the movement of wind or the draught in that room, that should also be constant. And you just say that you'll do exactly what the examiner is talking about, that you wrap around these different thicknesses of insulation and you note the temperature drop. So how the values look like in this case, again, my table of values always includes serial number, but this is not really required. What is required is the rest of this table along with their proper units. So thickness in centimeters of the insulation, starting temperature in degrees Celsius, final temperature in degrees Celsius, and subtracting the two gives us the temperature drop in degrees Celsius. And the last line is also always going to be the same, that you plot a graph of thickness versus the drop in temperature to make your final observations. So that was paper 62. Again, in my opinion, not really difficult. It was really straightforward. And if you look at one of these, actually have a look at both of these 2023 IGCSE paper sixes, so paper 62 and 63, and you'll find that these are really very similar to those. So again, yeah, ATP is not really all that difficult. Once you have enough practice, you just get the hang of it. There's no other way to really put it. So yeah. So thank you guys. Best of luck for your exams. As you just saw, ATP is really easy, so I suggest do not stress it out. Just read as many examiner reports as you can to know what errors you have to avoid, what the examiner looks for, and you'll be good to go as far as your ATPs are concerned. So thanks for your time and see you next time. Bye.